Hello, this is a presentation I did at ATCM, Asian Technology Conference in Mathematics in 2010. This conference is for math teachers who love using computers in their classrooms. And my topic was finding Taylor series by your eyes with GeoGebra and MuPAD, which means that you can find Taylor coefficients with your eyes if you use GeoGebra and MuPAD. This is a formula of Taylor series. And these are examples. Example 1, Taylor series of y equals sine x around x equals 0. Sine x equal x minus x cubed over 3 factorial plus x to the power of 5 over 5 factorial, blah blah blah. And this series converges from minus infinity to infinity. Let's check it with GeoGebra. This blue curve is y equals sine x. This is the first series of Taylor series, first polynomial of Taylor series, y equals x. For n equal 2, for n equal 1 and n equal 2, so second polynomial and first polynomial is same because the second coefficient is 0. Because y equals sine x is odd function. So the second coefficient is 0. Thus, second polynomial and the first polynomial is same. But third polynomial is different. Y equals x minus x cubed over 3 factorial. As n increases, the series converges in wider range. Actually, it converges from minus infinity to infinity. And you can magnify these graphs very easily with GeoGebra. And if you want to see more sequences, you can easily change the limit of n from here, interval max. The next example, Taylor series of y equals log 1 plus x around x equals 0. There is a big difference here because log 1 plus x is expressed by this sequence. But this sequence converges only from minus 1 to 1. So outside of this area, the series doesn't converge to y equals log 1 plus x. It diverges. So let's check it with GeoGebra. Second chapter, main chapter, finding Taylor coefficients by your eyes. First example, Taylor series of cosine x order 2 around x equals 0. First, you have to find tangent line. First approximation, a linear approximation near x equals 0. And tangent line to y equal fx is y equal 1. So the first approximation of cosine x is 1. This means 0x plus 1. Linear approximation. To find the second approximation, we have to subtract this first approximation from fx, because first approximation is a big approximation. So unless you deduct this from fx, you can't compare with ax squared. And after subtracting this first approximation, big chunk, we can compare r2x with ax squared. r2x means residue of the second grade. So let's check this with MuPAD. The blue curve is y equal cosine x, and green curve is y equal 1 minus ax squared. Now a is 0. And we are going to increase a to find the best approximation of y equal cosine x around x equals 0. To my eyes, 0.45 or 0.47 is the best solution. But to check it, we have to magnify around x equals 0. And this one is the magnifying glass, which I talked before. And unfortunately, GeoGebra doesn't have this. As you can see, if you magnify, you can find differences or gaps between two graphs. So we are going to change the number of a. Okay. Now they look very, very similar. So again, we are going to zoom this. They look identical, and we are going to check the number of a, 0.49. So this means that y equal cosine x nearly equal y equal 1 minus 0.49 x squared. The real number is, the real second approximation is 1 minus 0.5 x squared. It's very close. So we can find Taylor coefficients with computers and with our eyes. So near x equals 0, the right one, a equal 0.49, approximates fx better than the left. You may think that the left one is better than the right one, but you have to look very closely near x equals 0. And so we can tell that when x equals 0, cosine x minus 1 nearly equal 0.49 x squared, nearly equal half x squared. So we can get the second approximation of cosine x. This is a rough proof. Limit x to 0, 1 minus cosine x, x squared equal by multiplying 1 plus cosine x to both denominator and numerator. Limit x to 0, sine x squared over x squared 1 plus cosine x equal limit x to 0, sine x over x squared 1 over 1 plus cosine x. And as x to 0, x sine x over x converges to 1 and cosine x converges to 1. So the value of this limit is a half. Therefore, near x equals 0, 1 minus cosine x, x squared, nearly equal a half, which means cosine x nearly equal 1 minus a half x squared. So we can get second order Taylor series near x equals 0. But of course, this is a rough proof. A second example, and this is the last example of my presentation. Taylor series of fx equal exponential x order 3 around x equals 0. A tangent line to y equal exponential x at point 0,1 is y equal 1 plus x. So the first approximation is 1 plus x. And to get the second approximation, you have to subtract the first approximation like we did in the example 1. So we make R to x second order residue fx minus first approximation equal e exponential x minus bracket 1 plus x bracket, and compare this with ax squared. So let's do this with MuPAD. The blue curve is y equals exponential x, and the green one is y equal 1 plus x, tangent line at point 0,1, and the first approximation. And these gray vectors are the differences between exponential x and y equal x plus 1, and we are going to align the start point of these vectors along x-axis. And this blue curve is y equal exponential x minus bracket x plus 1 bracket. This is the second order residue, and we are going to compare this with ax squared. So this blue curve is exponential x minus bracket x plus 1 bracket, the second residue. And this one is y equal ax squared. Now a is 0, and we increase a. So this time, it's very difficult to find the fitting curve for residue 2. But strangely and amazingly, if we zoom around x equals 0, we can find a good enough approximation for R to x. Let's do it. Okay, so both curves look very similar to y equal ax squared. It's not perfect, so we are going to magnify these graphs again. Okay, one more. Okay, let's check the A. The number of A is 0.51. Theoretically, it should be zero point 0.5. So again, we could find the second approximation of exponential x. So this time, we are going to find the third Taylor series. To find that, we have to subtract the second approximation. The second approximation is this one, 1 plus x squared over 2, as we just did. This is the second approximation, and we have to subtract this second approximation from y equal fx. First, we are drawing exponential x minus bracket 1 plus x squared over 2. This is the third grade residue. We extract the second approximation from fx. And we are going to compare this function with ax cubed. It's very difficult this time. So we're going to magnify around x equals 0. Okay. Now as you see, both graphs looks very identical around x equals 0. And once they look identical, even if you magnify more, they look identical. Okay, let's check the number of A. The number is 0.16, nearly 1/6. Theoretically speaking, it should be 1/3 factorial, which is 1/6. So it's almost equal to the theoretical number. So thus we can get the third Taylor series by our eyes. So let's review. So we get the second approximation, and to get the third approximation, we subtract the second approximation from fx, which is this one, third residue r3x, and we compare this r3x with ax cubed, and with our eyes, by our eyes, y equal 1/6 x cubed looks closest to r3x. So exponential x nearly equal 1 plus x plus a half x squared plus 1/6 x cubed. And this is the third approximation of exponential x. This is fx. Assume this is fx. The first approximation is a big one, the biggest part. And we subtract this biggest part from fx, and we call it remainder r2. And we compare this remainder with ax squared. And we find that it can be approximated by x squared over 2 by our eyes. And this is the main part of R2. This one is the main part of R2. And we subtract this main part from R2, and we call it remainder R3. And the main part of remainder R3 is x cubed over 6. And we subtract this one, then we get R4, remainder R4. And the main part of R4 is something ax to the power of 4. Thus, we can continue this sequence, and we can get Taylor series by our eyes. But I have to admit that as n increases, it gets more and more difficult to find the Taylor coefficients with our eyes. So we need to know how to calculate. This is also a review by animation. So we get this one. This is R2x. This is this is the first approximation, and we subtract this first approximation from fx, and we get R2x. And we compare R2x with ax squared, and a is about 0.5. So the second approximation is 1 plus x plus 0.5x squared. And again, we subtract this second approximation from y equal fx. Then I get this r3x, the third remainder. And we compare this with ax cubed. And we get that y equal about y equal 1/6 x cubed is the best solution for approximation for R3. So we can get the third Taylor series by our eyes. Chapter 3, a proof of Taylor series. This chapter is a kind of appendix, but it has a lot to do what we have seen so far. We use Cauchy's mean value theorem. This mean value theorem is an expansion of the normal mean value theorem. If fx, gx are differentiable on open interval ab and continuous on closed interval ab, then there exists xi such that fb minus fa over gb minus ga equal f prime xi over g prime xi, and xi is between a and b. And there is a geometrical interpretation which is very easy to understand. We make a parametric curve C by x equals gt, y equals ft, this blue one. And we take 3 points, point A and B and P. A is a point on C for t equal A. B is a point on C for t equal B. And P is a point on C for t equal xi. Then the left side of this equation is the gradient of the line AB, this one. And the right side is, by the theory of differentiation, is the tangent at P. So this theory means that there is a point on C where tangent line is parallel to line AB. And this is trivial, and it looks true for any differentiable curves like this one. In this case, we can take two P's. One is here, the other is here. So geometrically speaking, so it is very trivial. And it is very easy to memorize this. To apply this theory, what you have to do is to differentiate both numerator and denominator and replace b and a by xi. Xi is between a and b. Now we are ready to prove Taylor theorem. But we are going to do that only for n equal 2 and 3. For n equal 2, suppose f w prime x exists in an interval around a, then for x in the interval, we define rx and gx as such. And this is the first approximation, because this is a tangent line at point A, fa. And we subtract the first approximation from fx. So this rx is the second remainder. And we define gx by this, x minus a squared. Since ra and ga equal 0, rx minus ra over gx minus ga equal rx over gx, this one. And we use Cauchy's mean value theorem. So we differentiate numerator and replace x by x1, f prime x1 minus f prime a. And we differentiate denominator and replace x by x1 to x1 minus a. And we get this. And we can use normal mean value theorem. By normal mean value theorem, this is equal to fw prime xi, and xi is between x1 and a. So we get rx over gx equal a half fw prime xi, and xi is also between a and x. That's why I wanted to show you this proof, because in the chapter 2 we found the ratio of these two values by i's, and here we calculated it. So the difference between chapter 2 and chapter 3 is either you do it with your eyes or do it by your mind. And this proof is taken by a textbook I learned in a university, and I was inspired by this proof. So I wanted to make a computer graphics. So to support this proof. So now we get this second order data series, and this is a strict proof. And for n equals 3, it's almost same. This is a second approximation, and we subtract the second approximation from fx. So this Rx is the third remainder, and we compare Rx with gx equal x minus a cubed. So Rx over gx is this, and we apply the Cauchy's mean value theorem once and twice, and apply the Cauchy's mean value theorem or normal mean value theorem again, and we get this, and then we get this, the third order data series. So you can download MuPAD and the GeoGebra files from my website. So I hope I can see you again. Bye.